3.7 Lesson 1, Derivatives of Composite Functions, the Chain Rule. And we'd also like to take a look at the derivatives of the sine and cosine functions. So if you look at our objectives, the first two objectives are just for you to know. The first objective, you'll know that the differentiation rule for f of x is equal to sine x is established using the definition of the derivative as a function. Objective 2, you will know that the chain rule is established using the definition of the derivative at a point, x is equal to c. The point that I want to make is we started learning about differentiation rules such as the power rule and how to find the derivative of a sum of functions, how to find the derivative of a constant times a function, how to find the derivative of a constant function. All of these differentiation rules ultimately are established on the definition of the derivative. So we're learning new differentiation rules today about how to find the derivative of the sine and cosine functions and something called the chain rule, which will help us to find the derivative of composite functions, but all of these differentiation rules go back to the definition of the derivative. And our third objective is you will know when you have the function f of x is equal to sine x, the derivative f prime of x will be cosine of x. And when you have the function f of x is equal to cosine x, the derivative of cosine x will be negative sine x. And the main part of today's lesson is objective 4. You'll be able to identify composite functions and find their derivatives by using something called the chain rule. And the vocabulary that we will be using today is composite function. That's something that we reviewed during the first week of the course, composition of functions. And when we talk about composite functions, there is, if you have a composition of two functions, you have an inside function as well as an outside function. The inside function is the function that goes to work first, and the outside function goes to work second, taking outputs from the inside function and doing something with those outputs. The chain rule is a differentiation rule that helps us to find derivatives of composite functions. Now we will briefly discuss the proof of the differentiation rule for f of x is equal to sine x. All of the details will be available for you to look at, but I just want to give you an overview. In fact, in your textbook, the proof is presented in section 3.8. So if you have the function f of x is equal to sine x, the derivative of the sine function is cosine. So if you have the function f of x is equal to sine x, its derivative is cosine x, as written here. The derivative with respect to x of sine x is cosine x. And of course, as we already saw in our lesson objectives, the derivative with respect to x of cosine x is negative sine x. So what you see here is the proof of the first rule, the derivative of the sine function. How does the proof of this differentiation rule start? It starts with the definition of the derivative that we learned previously in section 3.4, the derivative as a function. We define the derivative of a function as the limit of this difference quotient. So in our case here, our function f of x is going to be sine x. So when you form this difference quotient, we have three parts to it. We have delta x in the denominator. We have minus f of x, which would be minus sine of x. And then we have f of x plus delta x, which would be, our function is sine x, so we will have sine of x plus delta x. So you see that difference quotient. We're taking the limit of that difference quotient as delta x approaches 0. Why do we start that way? Because that is what we mean by derivative. This is what a derivative is, by definition. The next step in this proof is to rewrite sine of x plus delta x using a sum formula from trigonometry, which is a trig identity. It's a sum and difference formula. If you look at the first one, if you have sine of u plus v, you have plus or minus. In our case, we have plus because we have x plus delta x. So if you have sine of u plus v, that is sine of u times cosine of v plus cosine of u times sine of v. And that difference, that sum formula is used to rewrite sine of x plus delta x, as you see here. And then some algebraic manipulation is done. We take this term and move it to the front. And then the other two terms, we do some algebraic manipulation. What you have is negative sine x plus sine x times cosine of delta x. And we factor out negative sine x from each term. So when we do that, we'll be left with 1 from the first term, and we'll be left with minus cosine of delta x from the second term. And you might be wondering why this is done. It's actually something that will become apparent as we go through the remaining steps. It also involves some things that you haven't learned yet. So this is something that you see right here. That's where that comes from. There is further algebraic manipulation. You have a fraction here, and in the numerator you have a minus sign. So you can write that as a difference of two fractions. And then furthermore, with the first fraction, you can write sine of delta x over delta x, which you see here, and then multiplied by cosine of x. And with the second fraction, you can write 1 minus cosine of delta x over delta x, which you see here, multiplied by sine x. The next step is to recognize that you have the limit of a difference of two functions, or you can say the sum of two functions if you write plus and then the opposite of all of this. And then you can use a limit rule for finding the limit of a sum of two functions. So you just take the limit of the first function and add to that the limit of the second function, or in our case, subtract the limit of the second function. You're taking the limit as delta x is approaching 0, so cosine of x does not have delta x, so you can think of that as a constant with respect to delta x. And same thing here, sine of x does not have delta x in it, so you can think of that as a constant with respect to delta x, and have that factored out of each limit. And finally, you get to what you see here. Now, these are limits that you haven't learned about yet. You'll actually see this limit in section 3.8, but these are limits whose values are known in calculus. So when you have the limit of sine x over x, when the arguments are when the argument of the sine function is also appearing in the denominator, and you take the limit of that as the argument goes to 0, that limit is known to be 1. And if you look at special limit number 2, if you have 1 minus cosine x over x, and x is going to 0, that limit is known to be 0. So that's what you see here, rule number 1, and here, rule number 2. So that's how we know that the first one is 1, and the second limit is 0. And you can see here that you have sine of delta x, which is the argument of the sine function, divided by delta x, same as the argument, and it is the argument that is going to 0. Delta x is going to 0. So now you have cosine of x times 1 minus sine of x times 0, which is 0. So your final result is cosine x. And what is this? It's the derivative of sine x is equal to cosine x. The main thing that I want you to understand as we walk away from this particular part of the lesson is this. The derivative with respect to x of sine x is equal to cosine x is proved using the definition of the derivative, because that's what derivative means by definition. So we start the proof that way. Objective 2, you will know that the chain rule is established using the definition of the derivative of a function f at a point x is equal to c. So here we have the chain rule and its proof, and we will be taking a look at the chain rule later. But what I want you to focus on for now is that in the proof of the chain rule, look at what you have here. What is this? It is the definition of the derivative at a point. The function that we're working with when we're trying to prove the chain rule is h of x is equal to f of g of x. So that's our function. And you can see that we have a difference quotient here. We have x minus c in the denominator. And then we have minus the function evaluated at c. So our function is f of g of x. So we have f of g of c. And then here what we have is the function itself. So we have f of g of x. So we have the limit as x approaches c of this difference quotient from the definition of the derivative of a function at a point x is equal to c. So this will give us h prime of c. So I wanted to just point out to you that the chain rule that we're about to learn, that we're learning today, it is established using this definition of the derivative of a function at a point x is equal to c. We won't look at the details of this particular proof, but if you wanted to, it's there for you to look at. But the main thing that I wanted to emphasize is all of these differentiation rules that we're learning about, they ultimately come back to these definitions of the derivative as a function, or in this case, the derivative of a function at a point x is equal to c. Our third objective is just knowing that the derivative of the sine function is cosine, and the derivative of the cosine function is negative sine. So if you have a problem like f of x is equal to sine x, and you're being asked to find the derivative, you're going to write that the derivative is cosine x. If you have a problem like g of x is equal to cosine x, and you're being asked to find the derivative, you're going to write g prime of x is equal to negative sine x. So, and we already looked at the proof of this particular differentiation rule, and it was proved using the definition of the derivative as a function. Now we get to objective 4, which is the main part of our lesson for today. You'll be able to identify composite functions, and that was one of our review lessons that we did during the first week, so you can go back and watch that. And find their derivatives using the chain rule. So vocabulary, composite function, composition of functions, inside function, outside function, and the chain rule. We're going to work with these three functions for our objective. We have three functions. Y is equal to sine of 7x, y is equal to sine cubed x, and then we have y is equal to the square root of cosine x. Each of these functions are a composition of two functions. So we'd like to begin by understanding for each composite function how the two functions are composed. Which is the inside function? Which is the outside function? The inside function is the function that goes first. The outside function is the function that goes second. So a critical skill for you to have to be successful finding derivatives of composite functions using the chain rule is to be able to see in a composite function what the individual functions are and identify which of the individual functions go first and which of them go second. Which of them goes second. So let's take a look at number 1. You may be able to determine just by visual inspection that we have two functions here. The inside function is sine x, and the outside function, the inside function is 7x, and the outside function is sine x. I would like to show you that the function y for number 1 is f of g of x. And of course you write that this way, f of g of x, which means you have f of g of x, and the inside function is g of x, which is 7x. G of x is 7x. And the outside function is sine x, so you have y is equal to sine, and you evaluate the outside function at the output from the inside function, which is 7x. And if you look at number 2, let's see what two functions we have. You should recognize that the two functions that we have are the sine function and the cubing function. Now you might have a question, which of these two functions is the inside function and which of them is the outside function? To help us see that, let's go ahead and see how the two functions are composed to give us sine cubed x. Another way you can write this is sine of x, and all of that is of course cubed. By the way, this is different. This is not equal to, y is equal to sine of x cubed. You've got to understand that in the function that I wrote here, we have x cubed for the argument of the sine function. So this would be like number 1, where the inside function would be x cubed and the outside function would be sine. But that's not what we have for number 2. We have sine cubed of x, not sine of x cubed. You can write sine cubed of x as you see here. This is an alternative way of writing it. This means you're taking your inside function, which is sine, and then you're cubing it. It is different from what you see at the bottom of the screen. So writing it this way may help you to see that the outside function is whatever the input is, you cube it. That's the outside function. And the inside function is sine of x. So now we'll go ahead and see how the two functions are composed to give us the composite function y is equal to sine cubed x. So we have y is equal to f of g of x, and we have y is equal to f of g of x. And what is g of x? That's our inside function. It is sine x. And what is f of x? That's our outside function. Whatever input it gets, f will cube it. So now we take sine x, and we're going to cube it. And you can write that either like we have here or like we have here. Either way is fine. They mean the same thing. So we have sine cubed x. Let's take a look at our third function. Y is equal to the square root of cosine x. And again, like we saw with number 2, you can write this function in an equivalent format. We know that taking the square root is the same as raising to the 1/2 power. So you can write this as cosine to the 1/2 power of x, which you can also write as cosine x and then put brackets there, raised to the 1/2 power. However, it is different. It is not equal to cosine of x to the 1/2. that is different from what you have here. So it is not equal to that, because here the inside function would be the square root of x, and the outside function would be cosine. But that's not what we have for our problem. For our problem, the inside function is cosine, and the outside function is the square root function. So this is not the same as what we have. So now we'd like to understand how the two functions are composed to give us our composite function. So as you understand now, the inside function is cosine x, and the outside function is the square root of x. So our two functions are, the outside function is x to the 1/2, or the square root of x, and the inside function is the cosine function. So we have y is equal to f of g of x. So we have y is equal to f of g of x. Y is equal to f of g of x is cosine x. And what does the function f do with whatever input it gets? It takes the square root, or raises it to the 1/2 power. So we have cosine x to the 1/2 power. So that's what we have for number 3. So we've talked about pre-calculus, just understanding composition of functions. But now we're going to do calculus. We're going to use the chain rule to find the derivative of each of our 3 composite functions. We would like to begin by looking at number 1. So we begin by looking at the chain rule, and we're going to look at what we have here. You can write it in one of 2 forms. You have something called dy dx form, and we're going to look at the f of x form. So they're the same thing, just written in different, just expressed using different mathematical notations. So we're going to look at the f of x form. So if you have a function f of x, and it is a composition of 2 functions, and in fact, let me just write it this way here. If you have y is equal to, it's the same thing. I'm just sort of making it consistent with our usage of f and g in 1, 2, and 3. But this is the same thing that we're looking at now. If you have y, and it is a composition of 2 functions f and g, so you have y is equal to f of g of x. So what does the chain rule tell you? It tells you how to find the derivative of this composite function. It states that y prime is equal to the derivative of the outside function evaluated at the inside function multiplied by the derivative of the inside function. That's what the chain rule states. And I wanted you to see that, especially I wanted you to focus on the words that I said, which are stated here in outside function, inside function form. To differentiate a composite function, differentiate the outside function with respect to the inside function, and notice here that the inside function does not change, then multiply by the derivative of the inside function with respect to x. And that's what we're seeing here. So we have 2 functions. We have an outside function, which is f, and we have an inside function, which is g. The derivative of this composite function is, look at the words, the outside function is the derivative, differentiate, right? Differentiate the outside function with respect to the inside function. So we take the derivative of the outside function, evaluate it at the inside function, and then we multiply by the derivative of the inside function with respect to x. So the inside function is g, and we multiply by the derivative of the inside function with respect to x. So I'm just going to focus on these words here, and I'm going to write this at the top of my screen. So if you have a composition of 2 functions, and g of x is the inside function and f of x is the outside function, the chain rule says that the derivative of the composite function is the derivative of the outside function evaluated at the inside function multiplied by the derivative of the inside function. So let's apply that to number 1. So number 1, we have y is equal to sine of 7x. We know that the inside function is 7x and the outside function is sine x. So using the chain rule, the derivative of y is the derivative of the outside function, and we learned that the derivative of the sine function is cosine. So we're going to have cosine of 7x. We evaluate the derivative of the outside function at the inside function, and then we multiply by the derivative with respect to x of the inside function. So that's what we have. So y prime is equal to cosine of 7x multiplied by the derivative of the inside function, which is of course just 7. Now we prefer to write this as 7 times cosine of 7x, and we're done. That's how you do number 1. So now we take a look at number 2, and we have a composite function. So to find the derivative of this composite function, we will use the chain rule. And the chain rule says if you have a composite function, you take the derivative by finding the derivative of the outside function and evaluating that at the inside function, and then multiplying by the derivative of the inside function. So for number 2, we have y is equal to, the inside function is sine x, and the outside function is x cubed. So to find the derivative of this function, we use the chain rule. We start by finding the derivative of the outside function evaluated at the inside function. And of course, our outside function is f of x is equal to x cubed. So to find the derivative of the outside function, you will use the power rule. So you will have 3, and then you have to evaluate the derivative of the outside function at the inside function. The inside function for us is sine x. So you normally would write 3x squared for the derivative of f of x is equal to x cubed, but the inside function in this problem is sine x, so you will actually write 3 times sine x squared. It's like 3x squared, but remember, the chain rule says you evaluate the derivative of the outside function at the input of the inside function. So in place of the input here, you write the inside function sine x. So you have that, and then you multiply by the derivative of the inside function. So what is the derivative of the inside function? You have to find the derivative with respect to x of the inside function. And of course, we know that the derivative of sine x is cosine x. So now you're going to write, we know the derivative of the sine function is cosine x. So we're going to have 3 times sine of x squared, which you can also write as sine squared x. And then the derivative of sine is cosine, so I'll write that in red just so you can see that it's coming from there. And there's our final answer for number 2. Let's take a look at number 3 and how we would find the derivative here. So let's look at the chain rule once again. So for our third example, our function is y is equal to the square root of cosine x, which you of course can write in different ways, and perhaps this is the easiest way for you to understand which is the inside function and which is the outside function. The inside function is cosine x, and the outside function is x to the 1/2 or the square root of x. So to find the derivative of this composite function, we will use the chain rule. So y prime is equal to the derivative of the outside function evaluated at the inside function. Our outside function is f of x is equal to x to the 1/2. You can find the derivative of that outside function by using the power rule. Bring the exponent of 1/2 to the front. So we're going to have 1/2. Normally you would write x here, right? But the chain rule says find the derivative of the outside function and evaluate that at the inside function. So normally you would write x, but here we have to write the inside function, and you're going to write cosine x because that's our inside function. So what does the power rule say? It says bring the exponent to the front and subtract 1 from the original exponent. 1/2 minus 1 is negative 1/2. So I will get negative 1/2 for my exponent. And now I have to go to this part of the chain rule. I will now multiply by the derivative with respect to x of the inside function. And of course, what is our inside function? Our inside function is cosine x. So now I multiply by the derivative with respect to x of the inside function cosine x. So now we write y prime is equal to, if you would like to simplify, you can, and here's one way you can simplify. Whenever you have a negative exponent, you can take the power from the numerator to the denominator, and the exponent will become positive. So when I do that, I will have 1 in the numerator over, you have this 1/2, so you have 2 here, and then you have cosine of x to the positive 1/2 power. And then you're multiplying that by the derivative of the inside function. The derivative of cosine is negative sine x, as we learned today. And I'm going to write that here, negative sine x. And of course, you're multiplying what I wrote in black by what I wrote in red. And what I wrote in red, you can write that as over 1. So you're multiplying two fractions. So you can actually just multiply the numerators and multiply the denominators. And when you do that, you will have negative sine x here in the numerator. And multiplying the denominator by 1 won't change it. And the last thing that you can do if you wanted to simplify the answer is, in the denominator you have cosine of x to the 1/2 power. But raising to the 1/2 power is the same as taking the square root. So you can write the denominator as, instead of cosine of x to the 1/2 power, you can write that as the square root of cosine x. And this here is our final answer that I am boxing in blue. Well, let's box it in gold. That's our final answer. That's the derivative. So today, our main focus for today's lesson was being able to identify composite functions and finding their derivatives using the chain rule. And we had these vocabulary terms that we used throughout the lesson. Prior to getting to the main part of the lesson, we looked at objectives 1 and 2, where you understood that differentiation rules that we're learning and using are established from the definitions of the derivative as a function, or in the case of the chain rule, the definition of the derivative of a function at a point. And we also used these two differentiation rules. The derivative of sine x is cosine x, and the derivative of cosine x is negative sine x.